Okay, so we've got, and today is, of course, 2/24. We had mentioned Newton's second and third law. One of the big sort of takeaways from this, and this is Newton's third, when you've got two objects that are interacting, they exert equal and opposite forces on one another. You've heard that before. You're exerting a force on the floor is exerting a force back upward on you. You're exerting a force on your chair, the chair is exerting a force back up on you. There's an equal and opposite reaction. We call them action-reaction pairs. Many years ago, I remember a sophomore, at the time we taught physical science to sophomores, who just could not, for the life of him, understand how then when he threw a ball and the ball went forward, he said, but if there's an equal force on me, why don't I go backwards? Because you have more mass. You have a lot more mass, and therefore you don't move as much as the object with smaller mass. Okay, so this is where your book, this is the fourth section of chapter 4 in your book, and this is where they decide to introduce the concept of weight, force of gravity, and normal force. You can see why I do the little mini introduction early on. We've been using this for a while now. Before I kind of figured it all out, and I used to just sort of follow along with the book, it was always confusing because they go, oh, yeah, we haven't talked about that yet, but here it is. So your weight is the force exerted on you by Earth's gravity. Weight changes planet to moon to other planet to wherever. Your mass does not. Weight varies. Weight, the force of gravity, is always towards the center of the object exerting the gravitational force. We're on this nice massive hunk of rock, and that's the thing that's exerting the most obvious gravitational force on us. If we were out in space, presumably in a spacesuit, here's the thing, and we don't do Newton's law of gravitational attraction. All objects that have mass have gravitational attraction to one another. It just so happens that the Earth is so massive, the gravitational field of the Earth is so strong that we can't perceive the gravitational attraction of these two things. It's like standing in front of right in front of the speakers at the loudest concert you can imagine. The point where you feel your chest vibrating from the sound waves and then whispering to the person next to you. It's completely drowned out by the larger sound. And here the gravitational attraction between these two objects is totally overcome by the gravity of the Earth. If we tossed these two out into space and they were close enough, they would slowly and inexorably move together. But we can't observe that on Earth. We designate it as F sub G. You've been doing that for a while. Normal force. It's equal in magnitude to gravity or part of gravity. Sometimes, of course, it's just equal in magnitude to FGY. So that's an important thing to note. Please make sure that you fix that in your notes, because I really need to go back and edit these. They're old. We designate normal force as F sub n. I'm showing a lowercase n there, and I'm going to assume that I was looking at a good source when I did that, so we'll assume that's correct. I always forget if it's a lowercase or uppercase. So these are two of the everyday forces that we've been using in problems, and we've been using these since pretty much the beginning of the chapter. The one that we haven't been using, unless we're just given it as a force, is friction. So friction is a force that opposes an applied force, and friction is a force basically that opposes motion. There are two kinds of friction that we're going to talk about. There's static and kinetic. Static means to hold still. Kinetic is, of course, think about kinetic energy. Motion, kinetic is related to motion. And static friction only works when things are at rest. So the initial process of getting something moving is the process of overcoming static friction. Once it breaks loose and moves, sounded wrong, then you're no longer dealing with static friction, you're now dealing with kinetic friction. Because kinetic friction is the frictional force that's opposing the motion. In general, well, we'll talk about that in a second. So as long as you're putting a force on an object but the object hasn't started to move yet, the static friction is equal in magnitude to the applied force because it's not moving yet. Once we will start to talk about Fs max, that's static friction max. That's the amount of static friction that exists in the second before it breaks loose and starts to move. And once something is moving, the net external force is going to be equal to the applied force minus Fk. We'll do enough problems, you'll feel comfortable with that soon. So let me ask you this. Does it take more energy to get it moving or keep it moving? Who here has shoved something from a stop? Okay. Take more energy to get it moving or keep it moving? Getting it moving. Static friction for any surface object pair is generally greater than kinetic friction. Once you've got it moving, you don't want to let it stop because it's going to take less force to overcome kinetic friction than it will to overcome the static friction. And friction is entirely dependent on the surfaces involved. So for every surface object pair, we have a coefficient, what's called a coefficient of friction. It's the ratio of friction to normal force. And mu s is equal to the force of static friction max divided by normal force. Mu k is equal to kinetic friction divided by normal force. Okay, so anytime that we know coefficient of friction and normal force, we can calculate the force of friction. We'll do a sample problem together on 4C, and then I'll assign you some practice. Okay, so we have our picture. This is from the 4C sample problem in the book. These are problems where we don't necessarily start with the sum of forces because we need to know which axis we need to find the pieces from. So this is where we start to have the frictional coefficient equation, and we're looking to fill in gaps using the sums of forces. So we know that we're interested in finding the coefficient of static friction. And we know that mu s equals Fs max divided by Fn. So the applied force 75 newtons gets us motion. That's where suddenly it breaks loose and it goes. So what would the force of static friction max be? 75 newtons. That's what's going to get us our motion. So that's our Fs max. Now, normal force is not going to be quite as, well, it is straightforward on this one. It's not always. This is where we have to do a sum of forces on the y. It's not rising up into the air or sinking down into the earth. That's 0. Fn minus Fg, Fn equals mg. Okay, so we can actually do a substitution because they're so much fun. I'm going to shrink this. I'm going to move this over here. So it's a good habit to get into. So that's going to be F applied. This is going to be mg. So mu s will equal 24 kilograms times 9.81 meters per second squared, all under 75 newtons. What's our raw answer? Okay, we get a raw answer of mu s 0.31855, blah, blah, blah. What are the units here? Let's do the dimensional analysis on the little problem right here. Newtons divided by newtons. What are the units? There are none. It's a ratio. Ratios are by definition unitless. But it still freaks me out, and when I write the number, I'm like desperately scrambling and thinking, what units? No, it's unitless. So there are no units on coefficients of friction. Coefficients are unitless. When we sig fig this out, we get 2 sig figs, so mu s for this surface pair would be 0.32, and I still want to write a unit. Obviously, the lower that number, the lower the coefficient of friction. Do you think the harder or easier it would be to get something moving? Easier. And you can plug that, you can play around with that yourself for the same, well, you know what, let's do an extension on this problem. So let's do an extension on this problem and say, well, what if the coefficient of friction between this box and this surface was, instead of 0.32, what if it was 0.010? What applied force would be necessary to get this thing moving? Well, we know that mu s equals Fs max divided by Fn. Now we're being asked to solve for this. So mu s Fn equals Fs max. And if we are asserting that the coefficient of friction has decreased and it's now 0.10, we'll use our same normal force. We haven't changed the mass of the box. Oops. So what do we have? So it would only take 23.5 newtons of force to get the box moving. And if we look at that, that's actually fairly linear. So 23, well, it would actually be 24. 24 newtons would equal Fs max. We basically cut the coefficient of friction in a third, and lo and behold, the force required to move the box would be roughly a third of the original force needed to move the box. So what if we doubled the coefficient of friction, made it 0.64? It would take roughly twice as much force to get the box moving, and you can do the math yourself, but it is pretty linear. So it's, well, we'll talk about the other in a moment. So 4C on 145, all of those are assigned. So page 145, numbers 1 through 3, and I'll have the worksheet with key for you tomorrow. Questions?